Here we'll be addressing characteristic value problem by solving a simple example. And here we've been given a system matrix A, and we're asked to compute the eigenvalues and vectors and eigenvectors of the matrix using the identified methods. Some of the methods we already identified in our previous lecture. But to be sure that our computation from MATLAB is correct, I think it would be nice to first solve this problem analytically. And we already know that the eigenvalue problem is specified as AX being the same as lambda x. And then A minus lambda I, where I is the identity matrix, times X being the same as 0, is given as the system of equations describing the eigenvalue problem, so that the determinant of the system of equations equated to 0 is the same as the characteristic equation. And we already described in our previous lecture that the eigenvalue is sufficient to describe the system, largely because given the system, we're able to see that the eigenvalue is equivalent to the property that characterizes the system if the input to the LTI system is the eigenfunction. Then we have at the output, which is the response, being the same as the eigenvalue times the eigenvector. Hence, the eigenvalues that are associated with the eigenfunction of vector is sufficient to characterize that system. And as such, it is important for us to evaluate them. So in this case, A minus lambda I will be the same as 4 minus lambda, 2, 1, then 3 minus lambda. Okay? And if we should resolve the determinant of this expression, A minus lambda I, then that will give us the determinant of this, which will be the same as 4 minus lambda times 3 minus lambda minus 2 times 1. This will be the same as 12 minus 4 lambda minus 3 lambda. Is this times this, then plus lambda squared minus 2. So this is going to give us lambda squared minus 7 lambda plus 10. Okay? And then, since this is a quadratic equation, then we could use the almighty formula to resolve this, so that the characteristic equation given as lambda squared minus 7 lambda plus 10 being the same as 0 can be solved with the formula lambda being the same as negative b plus or minus square root of b squared minus 4ac divided by 2a. And in this case, a is the coefficient of lambda squared, which is 1, and b is the coefficient of lambda, which is minus 7, and c is the same as 10. And once we plug those in, then we have lambda being the same as negative 7 plus or minus square root of negative 7 squared minus 4 times 1 times 10 divided by 2 times 1. And this will be the same as 7 plus or minus square root 49 minus 40 divided by 2. That's 49 minus 40. Then lambda will be the same as 7 plus or minus square root of 9 divided by 2, which is the same as 7 plus or minus 3 divided by 2. So we have two values for lambda being the eigenvalues. Lambda 1 will be the same as 7 plus 3 over 2, which is 10 over 2, which is 5. And lambda 2 will be the same as 7 minus 3 over 2, which is 4 over 2, which is 2. So hence, lambda 1 is the same as 5, and lambda 2 is the same as 2. And having derived this, then we should be able to estimate the eigenvalues that are associated with the eigenvalues, the eigenvectors that are associated with the eigenvalues using the equation, state equation, S being the same as 0. So when lambda is the same as 5, then we have A minus 5i, that's 5 times the identity matrix, which would be the same as 4 minus 5, 4 minus 5, and 2, 1, 3 minus 5, which would be the same as minus 1, 2, 1, minus 2, all right? And then this should be equal to 0. So once we plug that into this expression, so we already solved for this, then we're going to have minus 1, 2, 1, minus 2, S1, S2 is the same as 0. Okay, so if we should evaluate the first row as this row, times this, so we're going to get for the first row, 0, 1. Then we have minus 1 times x1, that's minus x1, plus s2 is equal to 0. So technically, s2 is the same as s1, and this causes equality. And for row 2, we do the same thing. So 2 times x1, that would be 2x1, minus 2 times s2 would be minus 2s2, is the same as 0. And in this same way, this will cross this. Once this crosses the equality sign, so s2 is the same as s1. So from this, the eigenvector associated with the eigenvalue 5 will be the same as s1 being the same as 1, 1. Because s2 is the same as s1. So when s1 is 1, then s2 is the same as 1. Okay? Now, to normalize this, we can now normalize the eigenvector such that 1 over the square root of 1 squared plus 1 squared times 1, 1, which will be 1 over square root of 2. So the normalized eigenvector is the same as 1 over square root of 2, 1 over square root of 2. For lambda 1 being the same as 5. Okay? So S1 is equal to this. Now, we also know that lambda 2, the second eigenvalue, is the same as 2. So when lambda 2 is the same as 2, then A minus lambda I will be the same as 4 minus 2, 2, 1, 3 minus 2, which is the same as 4 minus 2 is 2, 2, then 1, 1. Okay? And once we plug that into the equation, S being the same as 0, then we have 2, 2, 1, 1, S1, S2 is equal to 0, 0, right? So if we evaluate at row 1, so that will give us 2S1 plus S2 is equal to 0. So in this case, S2 is equal to minus 2S1, right? And if we also evaluate at row 2, that's 2S1 plus S2 is equal to 0. So S2 will be the same as minus 2S1. So then S2, therefore, will be the same as 1 minus 2, since S2 is the same as negative 2S1. So when S1 is 1, then S2 will be minus 2. And then the normalized eigenvector will be the same as 1 over square root of 1 squared plus minus 2 squared times 1 minus 2. So this is 4 plus 1, that's 5. So that'll be 1 over square root of 5, 1 minus 2. So this will give us 1 over square root of 5, then minus 2 over square root of 5 as the normalized eigenvector. Okay. So now we've been able to evaluate the eigenvalues and the eigenvectors for this problem, such that the eigenvalues are the same as 5 and 2, and then the eigenvectors associated with this for 5 is 1 over square root of 2, 1 over square root of 2, and for 2, that is 1 over square root of 5, and then this is 2 minus 2 over square root of 5. Okay, so now we'll attempt a solution to the same problem using the MATLAB software to test methods like Sturm Liouville method, power iteration method, the inverse iteration method, and the QR method, even the finite element method, and the Rayleigh quotient method. So here we have the Sturm Liouville's method, where we have defined the system matrix and the identity matrix, and all the way. And for the Sturm Liouville's method, we already know that this approach literally discretizes the differential operator using the finite difference method, or the finite element method. And the resulting eigenvalue problem is then solved numerically. And once we run this program, so that is what we get. So we have our eigenvalues for the Sturm Liouville, which is 5 and 2. And then we have the normalized vectors based on the approximation of the method using the finite difference method. And when we look up the power method, so let's clear this. Now, when we look up the power method, we already know, based on our previous lecture, that this is simply a method used for iterative numerical that is used to solve the problem iteratively to evaluate the largest eigenvalue. So in literally running this program, then we are going to the MATLAB program is expected to return the value of 5, being the largest eigenvalue in terms of the magnitude. And that's exactly what we have, the dominant eigenvalue. Okay? So we see that the power method returns the dominant eigenvalue being the same as 5 and the corresponding eigenvectors. And for the inverse iterative method, it is literally used to find an eigenvalue that is closest to a given shift. So let's assume we identify a shift, then we want to evaluate the eigenvalue that is close to that. Now we have lambda being the same as 2 and lambda being the same as 5. And in this case, we have identified a shift 2.5, which exceeds the first. So now we expect this program to return lambda being the same as 5. Okay? And once we run this program, so let's clear this. To run this program, I see that it returned. Now, the inverse iterative method returned the eigenvalue that is close to sigma. And we already identified sigma to be the same as 2.5, which exceeds lambda equal to 2. And as such, we now know that the eigenvalue closest to this shift is 5. And then we also have the QR method. Okay, let us clear this. Now for the, let's wipe this also. So, okay. Now we know that the QR method is such that it iteratively decomposes the matrix into the product of the orthogonal matrix Q and the upper triangular matrix R. Okay, so that's what this literally does. And then it's able to perform the decomposition such that A sub K is the same as Q sub K, R sub K, until A sub K converges to the diagonal matrix. And then the diagonal matrix is the eigenvalue, okay, of the system. So with this method, we are able to compute the entire eigenvalues of the system. So it doesn't just return the dominant eigenvalue in terms of magnitude or the one that is closest to a particular shift, like the inverse iteration or iteration method or iterative method. But the QR method is used to evaluate the entire eigenvalues. And once we plot this, you'll see that the entire eigenvalues are returned. So let's just flip through. So here we display, okay? So, and that's it. Now that's iterative method I just plotted. This is the QR, yeah, this QR, okay? So we have the quotient, not the quotient now, the orthogonal matrix and the upper triangular matrix R, okay? And with that system, with the system of equation, we are able to resolve the diagonal matrix, which contains all the eigenvalues. And once we plot this, then we have all the eigenvalues returned in this process. So whenever we want to estimate the entire eigenvalues of the system, then the QR method becomes the choice. Okay. And then we also have the finite element method. And this method literally approximates the eigenvalues and the eigenfunctions of differential equations by discretizing the domain into finite elements, okay? And once that is done, the weak form is formulated, and then the stiffness, the global and the local stiff matrix are also computed, and then we're able to evaluate the system of equations. So this also gives us, well, some kind of good results. Yeah, see. And once we run this, yeah, we are able to evaluate our eigenvalues. And then we have one more, which is the Rayleigh quotient method. And now for the Rayleigh quotient method, which is about the last we're going to be addressing today, but not the least anyways. This method actually refines the eigenvalues and eigenvectors, okay, for the matrix by leveraging the Rayleigh quotient for rapid convergence, okay? So in this case, we start by the initial guess, say Y0. And then we now compute lambda naught being the same as Y0 transpose, A Y0, then Y0 transpose Y0. And at each iteration, we are able to solve the shifted system such that A minus lambda K times the identity matrix y sub k plus 1 is the same as y sub k. So that afterwards, we are able to estimate the y sub k plus 1, and then we normalize it. And after that, we are able to update the estimate by, say, y, or better still, the lambda, which is what we intend to solve. Lambda k plus 1 will be the same as y, that's the same way, sub k plus 1 transpose a y sub k plus 1 over y sub k plus 1 transpose, then y sub k plus 1. So once we do this, we are able to arrive at our answer. But the interesting thing about the Rayleigh quotient method is fast convergence. Okay, and if you want to achieve fast convergence near a target eigenvalue, and then this just does the job with high level of accuracy, especially for symmetric matrices. So let's run this. And that's what it is. Okay, so the target eigenvalue in our case is 5, and then we also have the eigenvalue vectors estimated.